All right, in this video, we're going to be talking about parent functions. We've already been messing with some of these parent functions. They're called parent functions because they're the most basic form of the functions. They're not moved up, they're not moved left, they're not moved right, they're not moved any direction at all. They're not multiplied by anything. It is just the basic function. With these, you'll need to know the name, you'll need to know the equation. It's also going to ask you the different characteristics, so we'll state these as we go through. We'll state the domain, range, and symmetry as we go through these functions. So with our first function, it is called our linear parent function. The linear function is f of x equals x. So if I know f of x equals x, if it helps you, make a table. I'll try to make a table as we go through these as well. All right, so if I put in -2 for x, so if I put in -2 right there, the y value I will get out is also -2. If I put in -1, it'll be -1, 0 is 0, 1 is 1, 2 is 2. So that's why this is called linear, because if I were to graph those points, and they continue this pattern forever and ever, it creates a line, which is a linear function. It's a parrot, or a line with a parrot in it. Linear! Parrot line. Sorry. I'm so sorry. All right, so this is your linear parent function. All right, so now for the domain, it looks like it's going left forever and it's going right forever. So the domain would be -infinity to infinity. For the range, it is also going down and up forever. So we have -infinity to infinity. And then for the symmetry. Now for the symmetry, we haven't talked about this yet. There are three things that we can be symmetric about. We can be symmetric about the y-axis, if it looks like it's a reflection over the y-axis. If I were to fold the graph on the y-axis and it mapped onto itself, it looked like the same exact thing. It looks like it would be, if I put like a mirror right here on my pen, if that was a mirror, it would be reflecting the same image on both sides. It's not in this case. There is also x-axis reflection or symmetry. X-axis would be as if there were a mirror right here. The last type is origin. Origin is kind of the hardest to see, but something that was taught to me, which has been super helpful for my students in my classroom, has been if we flip our graph upside down. So notice, if I take the graph and I flip it exactly upside down, hey, looks the same. So if it looks the same, what this is doing is it's reflecting it over the x and the y axis. So it's folding it on the x-axis, it's also folding it on the y-axis. So it's doing two different directions, same time. Since it looks like the exact same picture, we know that this is called origin symmetry. It's rotating it about the origin, and it is symmetric about the point 0, 0. We'll see some more of these as we go, and I'll show you how they make sense as well. All right, the next one, which we've been messing with some as well, is the quadratic parent function. So with the quadratic parent function, again, I'll make a table for you guys. If I have -2, -1, 0, 1, 2. So notice I am squaring my x values. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So if I were to graph all of those points, this is also called a parabola, parabolic motion, and it kind of goes away. I can also do 3 squared is 9. Goes away like that. -3 squared would also be 9. So I have a quadratic equation. It's called a parabola as well. So now for the domain, it's going to the left forever. So we're going to assume that this keeps expanding and expanding and expanding as it goes out. So we're going from -infinity to infinity, also because there's no x values that I cannot have. Now for the range, the lowest y value we have possible is 0, and it is included. It is hitting right at 0, right? We can see that that is a point right there. So I have it going from 0 to infinity. Now for the symmetry, it looks like if I were to put a pen right there, that's kind of thick. Here, let me put a piece of string right there. Right? If I put a piece of string, it looks like that piece of string is almost like a mirror, and it's reflecting over the line, or the y-axis. So since it looks like it's a reflection over the y-axis, we call it y-axis symmetry. That's really what that is. That's it. That's all there is to it. All right, moving on. We have the absolute value parent function, which Apex has talked about a little bit, but now we're just going to go into more depth on it. Finally, hate that they talk about it without actually like working with you. All right, so remember the absolute value just means the distance from 0. So if I'm taking the absolute value of x, -2 is 2 units away from 0. -1 is 1 unit away from 0. 0 is 0 units away from 0. 1 is 1, 2 is 2. So what this does, if I have -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, it almost makes two linear functions going outwards. So I have one going that direction, the other is going that direction. So it's taking those negative values and making them positive. So it's essentially like the linear parent, except I took this bottom half, chopped it off, and I put it on the positive y values. So for the domain, it's still going left and right forever. There are no values excluded. For the range, it is going from 0 to infinity. Notice that 0 is included, because it is hitting at 0, 0. And then for the symmetry, it looks like, again, just like our parabola, if I were to put a mirror right there, it would be a reflection of itself. So I have a y-axis symmetry. All right, next one, reciprocal function. This one's a little bit tougher, so I'll do a few more points. We'll do x and y. I'm going to do -2, -1, and -1/2, 0, 1/2, 1, 2. All right, so if I put these values in, if I put in -2, it's taking 1 over that number, so this would just be -1 over 2. If I have 1 over -1, that would just be -1. If I have 1 over -1/2, that's going to create -2. 1 over 0 is undefined, so that is not even possible. So I won't have any values at 0 because I can't divide by 0. So if I do 1 over 1/2, that'll create 2. 1 over 1 is 1. 1 over 2 is 1/2. So now if I graph these points, -2, 1/2, -1/2 right there, and then -1, -1, -1/2, -2, and then I have 1/2, 2, 1, 1, 2, 1/2. So what's happening here is as my graph is going this direction, it's getting closer and closer to 0, right? Even if I did 1 over 99, so it flips the fraction and it would be 99, right? So it's getting really, really, really close to 0 in both directions, but it's never actually touching it. So it's getting closer and closer and closer. Now as it goes out forever, as my x values get increasingly large, so if I have 100, that would just be 1 over 100. If I have 10,000, that would be 1 over 10,000. So there's no number that I could get such that my y value would actually ever be 0. So what this part does is it gets closer and closer and closer to the line, but it does not ever actually touch. This part as well, it gets closer and closer and closer, but it does not ever actually touch. So what our graph is creating here, we may have talked about it a little bit, is something called asymptotes. An asymptote is essentially what our graph is approaching, but it can never touch. We have one here called the horizontal asymptote in pink. The horizontal asymptote is called so because it is going horizontal. Right, so it's going side to side. So we have something called a horizontal, A-S-Y-M-P-T-O-T-E, asymptote. No, it's asymptote. We have a horizontal asymptote, and we say it as the line y equals 0. So if we were to graph just a line, that line would be y equals 0. All right, our other one here is called a vertical asymptote, namely so because it's going vertical, it's going up and down. So we have a vertical asymptote. And again, asymptote is something that we cannot touch, especially the vertical asymptotes. Every now and then, something crazy will happen, especially if you get into pre-AP pre-cal, where we can actually be equal to a horizontal asymptote. The horizontal asymptote actually represents more so what it's going towards as it goes out and out forever. You'll learn later that this is called end behavior. But the horizontal asymptote we can cross, the vertical we can never cross, and in this case it would be x equals 0 because it's the x value that we cannot have. Now for our domain and range, for the domain, it is everything except for the x value that we cannot have. So we cannot have 0, so I'm going -infinity to 0. It's my vertical asymptote. And then from 0 to infinity from my vertical asymptote on. Now for range as well, I'm going from negative infinity all the way up, but I'm never actually equal to y equals 0 here. So I'll have to exclude that from my range. And then I go from as close as I can be to 0 all the way up forever. So my range is also negative infinity to 0 and 0 to infinity, somewhere in there. Now for the symmetry, it's not over the y-axis, it's not over the x-axis. If you turn your graph upside down, it looks the exact same. So that tells me that it is origin symmetry. Get back on it. There we go. Symmetry is origin. O-R-I-G-I-N. Origin symmetry. All right, moving on. I think we only have 2 more parent functions. Getting close. And then the last 2 sections of this are pretty easy. It's not too bad. All right, so now for our cubic parent function. So notice I am cubing numbers. So if I take negative 2 and I cube it, negative 2 times negative 2 times negative 2, that will create negative 8. Negative 1 multiplied by itself 3 times would create negative 1. 0 would be 0, 1 would be 1, 2 would be positive 8. So if I were to graph these points, I have 0, 0, 1, 1, 2, 8. So it grows super fast. Now I have negative 1, negative 2, negative 8. So what this does is it almost creates like a quadratic type, but it's growing a lot faster because I'm cubing. I'm not only squaring, I'm cubing the numbers. And I also go in the negative direction because I'm multiplying a number by itself 3 times. So a negative times a negative times a negative will still produce a negative. All right, so that's my function. So now for the domain and range, the domain is going left and right forever. There's no x values I cannot have. So I have it going negative infinity to infinity. And then the range is going up and down forever. So that's also going negative infinity to infinity. Cool background. You ready for this? It's the monkey. It's the space monkey. All right, sorry. All right, here we go. Keep going. Oh, wait, symmetry. Wait, don't tell me. First symmetry. It's not reflecting over the y, it's not reflecting over the x, but I can turn my picture upside down and have it look the exact same as my original. So what that means is I have origin symmetry. Origin symmetry. All right, last one. Cube root parrot function. So this one I'm going to pick more specific x values because I'm taking the cube root. So I need to think about what number times itself 3 times would give me the x value. So with that, I'm going to choose negative 8 because I know if I were to put in negative 8, negative 2 times itself 3 times would give me the negative 8. If I choose negative 1 times itself 3 times would be negative 1. 0, 0, 1, 1, 8, 2. And if you haven't picked up already, these are actually inverse functions of each other. So notice, the x's and the y's, right? Inverses, we just learned. They flip the x and y exactly where they are. So now I have a new table with the inverse operations. So here's where it actually creates the inverse operation. And I have it flipping over the line y equals x. Right, so it looks like the same thing, except it's kind of sideways. All right, so there'd be our cube root parent function. So now for the domain, there's no x values I cannot have. So I'm going negative infinity to infinity. And for the range, I know it's growing super fast, but trust me, it's going up forever and it's going down forever. So I'm going negative infinity to infinity. And then for the symmetry, it's not x-axis, it's not y-axis. I can turn it upside down and have it be the exact same thing. So it is origin symmetry. All right. Hopefully this video was helpful for you guys. Please, whatever questions you got, let me know. I'm only a click away in a few sentences, or if you ever want to set up a Zoom session, I'm here for you. Please, just let me know. All right, I'll talk to you all soon. Bye.